All right, this is video 3 for the energy and power unit. So to start us off with this one, I want to discuss power and energy. And one of the problems is that those two words are often used interchangeably. It's really unfortunate, but they often are. This is unfortunate, since items like TNT have low energy, but they can cause more damage since they have a higher power. Or items like cookies, which have more energy, but cause less damage since they have lower power. So I wanted to talk a little bit about some of these two topics a little closer. So first off, the unit power. The unit for power is the watt. It was named after James Watt, and he truly developed the science of the steam engine. And basically what Watt did, the way we define it is we say that 1 watt, which we use a capital W for, is equal to 1 joule per second. So then if I have a kilowatt, that would be the same thing as 1,000 joules per second, since kilo means 1,000. So that's some of the definitions for the watt. And again, we see the joule in here, and notice then that a joule can be the same thing as a watt times a second. All right, energy is conserved. You probably heard this in chemistry. Basically, if we take a chemical reaction like gunpowder, if I fire a gun, there's gunpowder inside of it that's suddenly turned into heat energy. And that the gases that come out are so hot that they expand rapidly. So the gunpowder, what it does is it heats up the air inside the muzzle of the gun, makes it really, really hot, and expands it, and it pushes the bullet out of the end of the gun. So in doing this pushing, you're losing some energy. It's cooling off. And that energy then goes into kinetic energy of the bullet. So if you add up all the energy, the kinetic energy of the bullet, the heat energy of the gas, all of that energy will be the same. It's that the chemical energy is being converted into heat and kinetic energy. But the number of calories after the gun is fired is exactly the same as the number of calories that was stored in the gunpowder. So, since the amount of energy is the same before and after the explosion, it is said to be conserved. We would get the same thing in a campfire. If I look at all the calories of energy in the wood, it would be the same as all of the energy of heat and sound and light that I would get as I burnt that log, as I burnt that wood. So this is so important. The law of conservation of energy is so important that we give it a fancy name. We call it the first law of thermodynamics. So when people and politicians say we need to conserve energy, what they really mean is that we need to use less coal, less gasoline, and other valuable sources of chemical energy. Because really, all of the energy we have has always been there. Now, it is very, very easy to convert energy into heat. It is very, very hard to convert it back. Okay, so when we go to measure energy, the easiest way to measure energy is to convert it into heat and then see how much it raises the temperature of water. In fact, when we take a look at the science calorie, 1 science calorie, which is the lowercase c, is equal to how much energy needed to raise 1 gram of water by 1 degree Celsius. So 1 science calorie, if I apply that energy to 1 gram of water, its temperature will increase by 1 degree Celsius. So that's a definition of a calorie. So if I were to think about a food calorie, which is 1,000 of those, it'd be what's needed to raise 1,000 grams of water by 1 degree Celsius. All right, so again, if I take a look at energy, the calorie, i.e. the calorie heats 1 gram of water by 1 degree Celsius. The food calorie heats 1 kilogram by 1 degree Celsius. And, 1 food calorie is the same thing as 4,182 joules or 4,200 joules. The joule is how much energy is needed to lift 1 kilogram by 10 centimeters, or to lift 1 pound 9 inches. The kilojoule, then, is 1,000 joules. Another way of thinking about it is a kilojoule is roughly 1/4 of a food calorie. Megajoule. The prefix mega means million, so it would be 1,000 kilojoules or 1 million regular joules. It costs about 5 cents from the electric company, 1 megajoule. Kilowatt hour. A kilowatt hour is 861 calories, so right around 1,000 food calories. It's 3.6 megajoules, and it costs 10 cents from the electric company. Okay, this next one you probably have not heard of. It's a British thermal unit. Unless you go into the heating and cooling industry, you probably won't use it. A BTU, in fact, maybe you've seen these when you buy like an air conditioner. It's rated in BTUs. So 1 British thermal unit is roughly 1,000 joules, or about 1/4 of a calorie. And then finally, a quad. It's a quadrillion BTUs. So that's even higher than billions, million, billion, trillion, quadrillion. And this would be the total energy the United States uses. So that the U.S. uses 100 quads per year. So 100 quadrillion BTUs per year. The entire world uses about 400. So the United States uses roughly 1/4 of the total energy the entire world uses. Okay, so that was energy. Now when we talk about power, power is the rate of energy transfer. So 1 gram of dynamite releases 0.651 calories in 0.000001 seconds. That's fast. So that gives it a power rating of 651,000 calories per second. So that's kind of a weird unit, but remember energy per time is the same thing as power. So we can measure power in calories per second, but the more common unit would be the watt, a joule per second. Another common one is horsepower. So 1 horsepower is 0.18 calories per second. So if you were to have a power output, let's say you're running or something, of 1 horsepower, you would be converting 0.18 calories of your food into 0.18 calories of kinetic energy every second. So that should give you an idea for how much energy you consume or burn off during exercise. A 1 horsepower is also 746 watts, but we'll just go ahead and round that to 1,000. So 1 horsepower is roughly 1 kilowatt. Okay, so let's take a look at some common examples here. So first off we have is a flashlight. A flashlight bulb is roughly 1 watt. So that would be 1 joule per second. If we compare that to a bright light bulb, let's say one in your house, or the heat from a person who's just sitting down, that would be 100 watts, or 100 joules per second. So that's something to think about. Your body's constantly producing heat to keep your core warm. So you have a power output of 100 watts without doing anything at all, which is really amazing. The next one is a horsepower. One horsepower, you can think of it as typical, typical horse, obviously. Or you can think of it as a human running upstairs. If you run upstairs, you are producing roughly 1 horsepower. So right around 1 kilowatt of power. Okay, let's say we have a small house. So a really small house will use roughly 1 kilowatt. So after 1 hour, the house has used 1 kilowatt hour of energy. After a full day, it has used 24 kilowatt hours of energy. This is also equivalent to roughly 1 square meter of sunlight. So that's like a small bed sheet. So again, this is roughly 1 horsepower. Okay, a very, very small car. 20 horsepower. And you may say, oh, well, my car's got 100 or 200 horsepower. That's true, but when you're traveling down the interstate, you're only using about 30 to 50 horsepower just to keep the car moving. So again, that's right, around 20 kilowatts. Okay, if we take a look at the electricity for a small town, so like Dresden, it takes about 1 megawatt. So that, again, is 1 million watts, or 1 million joules per second. That's also roughly the same energy. That's also the same energy as like a 747 plane or a very small power plant. 1 gigawatt. One gigawatt is 1 billion watts. This would be a large power plant. So the power plant at Conesville is not quite a gigawatt, but it's definitely more than just 1 megawatt. 400 gigawatts. That's the average power used by the United States. Two terawatts is roughly how much energy is used by the world, or electrical power, I should say. So that would be 2 times 10 to the 12th watts. It is a lot. Okay, so now I want to talk about some examples of power. But looking at the time for this video, I'm going to save that for the final video. So this will complete the video for this unit.